Welcome to Module 4 of LectureCast-Prolog. So far our rules have looked a fixed distance ahead. A grandparent rule chains two parent facts, a sibling rule checks two parents. But what if a relationship has no fixed depth, like ancestor, which can span any number of generations? To define a relation that reaches arbitrarily far with only a few lines of code, we need recursion. In this module we will see how a clause that refers to itself can define something effectively infinite, and how Prolog actually runs it. Let us place today in the arc of the course. Module 1 gave us the declarative idea, state what is true. Module 2 built the three pillars, facts, rules, and queries. Module 3 opened the engine and showed how unification and backtracking search for answers. Today we use that engine to do something new. Recursion is not a separate feature bolted onto Prolog, it is simply a rule whose body calls the very predicate it is defining. Everything you learned about matching and backtracking is exactly what makes recursion run. Here is the core move. A recursive definition refers to itself. Take the relation ancestor. An ancestor is either a direct parent, or a parent of an ancestor. Notice the word ancestor appears on both sides. That looks circular, and if we are careless it can be. But handled correctly it is not a trap, it is the most powerful pattern in logic programming. A handful of clauses, fixed and finite, can describe a relation with no fixed bound. That is what our subtitle means, defining the infinite with a finite program. Every sound recursion has two parts, and you should learn to spot both immediately. The first is the base case, the simplest situation, where the answer is known directly with no further recursion. The second is the recursive case, it handles a larger problem by doing a little work, then calling itself on a smaller piece. Think of descending a staircase. The base case is the ground floor, where you stop. The recursive case is one step down, then ask the same question again. Miss the base case, and you fall forever. Let us return to our family tree. We have parent facts, Lou is a parent of Pete, Pete of Ian, Ian of Lucy. The parent relation reaches exactly one generation. With grandparent we could chain two. But to ask whether Lou is an ancestor of Lucy, 3 generations down, a fixed chain of parent goals will not do, because in general we do not know how many generations lie between two people. We need a relation that follows the parent links as far as necessary, however deep. That relation is ancestor. Here is ancestor, in 2 clauses. The first clause is the base case, X is an ancestor of Z if X is simply a parent of Z. The second is the recursive case, X is an ancestor of Z if X is a parent of some Y, and that Y is an ancestor of Z. Read declaratively, the 2 clauses together say an ancestor is a parent, possibly several links removed. Read procedurally, to prove ancestor Prolog first tries the direct parent, if that fails it takes one parent step and recurses on the rest. Watch how Prolog proves ancestor of Lou and Lucy. It tries the base clause first, is Lou a direct parent of Lucy? There is no such fact, so it moves to the recursive clause. It finds parent of Lou and Pete, then must show ancestor of Pete and Lucy. Again the base case fails, so recurse, parent of Pete and Ian, then ancestor of Ian and Lucy. This time the base case succeeds, because parent of Ian and Lucy is a fact. The recursion has walked 3 generations down the tree and bottomed out. Each step made the problem smaller, and the base case caught it. Recursion is not about families, it is about any relation that chains. Here is a classic example. Is digesting. An animal is digesting some food if it just ate that food, or if it just ate something that is itself digesting that food. Look at the shape. Clause 1 is the base case, just ate, known directly. Clause 2 is the recursive case, one just ate step plus is digesting on the rest. It is exactly the same skeleton as ancestor, only the domain changed from parents to predators. Once you see the pattern, you will reuse it everywhere. Suppose a mosquito just ate blood, a frog just ate the mosquito, and a stork just ate the frog. Now ask, is the stork digesting blood? The base case asks whether the stork just ate blood directly. No. So we recurse, the stork just ate the frog, so is the frog digesting blood? Recurse again, the frog ate the mosquito, so is the mosquito digesting blood? The mosquito just ate blood, base case, true. The answer now propagates back up the chain. It is the same descend, bottom out, return rhythm as the family tree, on a completely different relation. Recursion also works over numbers, and here the shrinking is easy to see. Consider counting down, countdown of 0 prints liftoff and stops, the base case, countdown of n, for n above 0, prints n, computes n-1, and counts down from there. Or take factorial. Factorial of 0 is 1, the base case. Factorial of n is n times the factorial of n-1. Each call uses a strictly smaller number, marching toward 0. With numbers the rule for safe recursion becomes concrete, every recursive call must move closer to the base value. Let us run factorial of 4 and watch the call stack. To get factorial of 4, Prolog needs factorial of 3, for that, factorial of 2, then factorial of 1, then factorial of 0. Each call waits, stacked, for the one below it to finish. At 0 the base case fires and returns 1. Now the stack unwinds, 1 times 1 is 1, 2 times 1 is 2, 3 times 2 is 6, 4 times 6 is 24. Notice the two directions. Going down, the problem shrinks to the base. Coming back up, the answers multiply together. A few lines to find a computation of any depth. Every recursion you will ever read follows the same three-phase shape, and tracing it by hand is the fastest way to trust your code. Phase 1, descend, each recursive call replaces the goal with a slightly smaller one. Phase 2, hit the base, the smallest case matches a fact or a simple test and stops the descent. Phase 3, return, results travel back up through the waiting calls. To watch this live in Prolog, you can sprinkle a write inside the recursive clause, or use the built-in trace. If the descent never reaches the base, you have a missing or unreachable base case. From all of this come 3 iron rules for writing recursion that terminates. 1. Put the base clause first, so Prolog checks the stopping condition before it dives. 2. Place the non-recursive goal before the recursive call, so real work, like a parent lookup, happens before you recurse. The dangerous mirror image, calling the recursion first, can loop forever before it ever tests anything. 3. Make sure every recursive call shrinks the problem toward the base, a smaller number, a shorter list, a step down the tree. Follow these 3 and your recursion halts. Break the second one and you meet the infinite loop, which we dissect in Module 6. Let us gather it up. Recursion is a clause that calls itself, built from a base case that stops and a recursive case that shrinks the problem and recurses. We saw it define ancestor across any number of generations, drive as digesting along a food chain, and compute factorial through a rising and falling call stack. And we distilled 3 rules: base first, non-recursive goal first, always shrink toward the base. Next time, in Module 5, we put recursion to work in practice, over numbers, over lists, and over nested structures, the tools you will use in almost every real Prolog program. See you there.